Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Nicole Vassh with us today. Hi, Nicole.
Hi, Frank.
How are you?
I'm doing all right. Yeah.
Good, good. Have you had your first vaccination yet?
No, I have not. It's not eligible from what I've read, not yet. Yeah, but my parents have had one, so that's a bit of a relief for me. Yeah. Good. What about you?
I got my second vaccination about a week and a half ago now. So I'm happy about that. So that must mean I'm probably a day or two older than you are.
Well, it's different by state, right? It's different by state. Yeah. Okay.
You gotta love it. So Nicole, what's your geolocation? Where are you at?
I'm currently in Indiana, so I'm a postdoc at the University of Notre Dame.
Cool. Yeah. Very good.
So if you see the gray sky-ish background going on here, that's what's happening.
Well, equinox is around the corner, so yeah. The Midwest tends to, and I lived there for a while, tends to linger a little bit. Let's put it that way. Yeah. But equinox is around the corner, and so things will maybe start to turn the corner, and the crocuses will come up, and the leaves will come out, and it'll change.
Yes. Very much looking forward to that. Is it already super hot in Arizona?
No, actually, it's been fairly cool the last couple of days.
Nice.
Relatively speaking. So we've been, in the mornings, it's been getting into the upper 50s Fahrenheit. And if you insist, I can do a quick calculation on centigrade, Fahrenheit.
That's okay. Yeah.
Or Kelvin, if you like.
Yeah, why not? Why don't we use that more? Come on.
But we all use, right?
Yeah, right.
So no, the power switch hasn't been hit yet, so we haven't warmed up good. Usually the power comes on sometime around in May is when things start really getting toasty.
Okay.
So we still have another month or two of relatively cool weather, so try to enjoy it.
Okay.
Cool. So Nicole, what do you like to do for research?
So for research right now, my main focus is on the origin of the elements, and I do this through a nucleosynthesis perspective. So there are many ways to look at the origin of the elements: observation, simulation. There's a lot of different facets to trying to understand the origin of the elements, but specifically I do nucleosynthesis, so I kind of live at the interface between simulations, understanding what simulations mean coupled with the latest nuclear physics, and then compare to observation. So specifically, I do heavy element nucleosynthesis, rapid neutron capture currently.
Very happening field these days.
Very much so. Lots to look at.
That is going to bring us to this really lovely APJ article on Markov chain Monte Carlo predictions of neutron-rich lanthanide properties as a probe of our process dynamics. And Nicole, take us away.
All right, so as Frank mentioned, our process is a pretty happening field right now. There's new developments in the wings here. So we know now that neutron star mergers are a source of heavy element production of the R process, but it's still unclear as to whether or not they are the dominant source within the solar system. So in this paper, what we're trying to look at is the dominant source of our process enrichment in the solar system by looking at solar system R process abundance residuals. Specifically, we look at the lanthanide elements, which are really key for merger observations and other things. But we look here specifically because there is a little feature in the abundances that's a curious little bump that's called the rare earth peak. And this little feature could be related to nuclear structure, and it's also very sensitive to the astrophysical environment in terms of how it could form. So it can tell you things about the nuclear physics and things about the astrophysics. So we're trying to take what we see from observation and go backwards to the nuclear physics and then compare with the latest experiment. So that's the basic premise of this paper.
Cool. Okay.
Okay.
Where would you like to go?
Yeah, so we can just keep going. I mean, just as I mentioned, this is a really timely opportunity with new observations in play, but also I just want to mention, so what Markov chain Monte Carlo is a statistical method. So this is something that also currently is really timely. There's a lot of development within statistical methods, machine learning, things like this. So we're exploiting advancements in a lot of fields here. So that's essentially what we discuss in the beginning. And then since you're going to try to work your way back to the nuclear physics, the opportunities within experiment are also blossoming at this time. People are able to probe more and more neutron-rich. The facility for rare isotope beams will be coming online. So we're going to be able to compare what we're doing in looking at the nuclear physics to what they find to say something about our process, lanthanide production. So let's get into the details of what that means. I mentioned the rare earth peak. So this little peak, let's go to figure 1, Frank.
Yes.
This little peak is between the R process second and third abundance peaks. I don't see figure 1, Frank.
You don't.
There it is. Okay.
We're going to be having a little bandwidth lag.
Yeah, I think we have a delay here, but okay, here we go. All right, so this is between the first and the second peak. So this is between the second and the third peak. The peaks are well established to be connected to nuclear structure, so shell closures. You have these neutron shell closures, you become extra stable, and you pile up material in that region. So this little bump here could have something similar going on, not a shell closure, but something that's giving you some kind of enhanced stability. So we're trying to understand what that could be. Well, if you look at what different models, these are different mass models here that are predicting the abundance that we use to predict the abundances, it varies quite a bit, what kind of structure you see, if you see any structure at all. So what we're trying to do is figure out what do you need from the nuclear physics side in order to actually match these solar abundances. Okay, so that's the figure 1. If you zoom out a little bit. Like more so. I want to see that first equation.
Got it.
Yeah. So the way that we're going to do this is we're going to use Markov chain Monte Carlo. This is where you take and you're going to modify some kind of property. Here we choose to modify the masses, the nuclear masses specifically within the lanthanide region. These are going to then feed back into our nucleosynthesis rates, things like neutron capture, things like beta decay. But specifically, we're going to use equation 1 here, where we take a model called Dufalo-Zucker that really just has like no nuclear features, nothing special going on in the lanthanide region. So it doesn't really pile anything up there and it doesn't form a nice rare earth peak. So we're gonna try to add on to this, what kind of mass corrections would you need in order to form that peak? And that's what that is there. So future plots that you're going to see from this work are the difference between our masses that we find and Dufalo-Zucker. And that's why, is because of this parameterization here. That's what we do. Okay. So these little ANs are what we're going to wiggle around. We're going to Monte Carlo them. We're then going to, if you go down, we're going to test whether or not our masses first are any good. We're going to do things like compare to AME data. Are we getting further away from known masses when we do these kinds of things? There we go. We're going to feed these into neutron capture rates and beta decay rates and photodissociation rates. You can see those equations right there. Yep. And how they depend on the masses, or how we model them to depend on the masses. That's separation energies, and masses will go into separation energies. And then we're going to run a nucleosynthesis calculation, and we're going to get a prediction for the abundances with our masses. So then we compare to solar data using a chi-squared. So this is all describing the kinds of chi-squareds that you get. And then you take a look at the likelihood function. It's essentially a ratio of your exponential of your chi-squareds. And so this is how we move forward, basically. We're informing our masses from the abundances, the solar abundances, given solar abundance uncertainties. Okay, so if you go down, we're going to go to the next figure.
Cloud. Purple clouds.
Yeah. the big figures.
Yeah, we definitely have a little bandwidth lag going on here.
Yeah.
It's okay. It's all good.
Okay, so this figure 2 here shows we have 2 runs. So the first, the top and the middle panel are different MCMC runs. And then the bottom panel is when we put 50 runs all together. So we decided to go with parallel chains method, MCMC. We found it to be most effective for what we were trying to do, to make sure that we're exploring the parameter space and converging upon something if we consider everything. So really that lowest panel there is the best representation. We've looked around, this is colored as a function of chi-squared. We've looked around the parameter space, which determine the masses, and we've found a preferred region. Basically, that's giving us low chi-squareds for our abundances. Mm-hmm. So how do we know when to stop? Well, we have a couple of different metrics that we look at. This is always kind of a tricky thing when you do anything with statistical methods. How do you know when to stop? How do you know you've converged? Well, figure 3 is one of the ways that we considered knowing that 50 runs was enough. So what we have here is the result when you just take 20 runs, 30 runs, 40 runs, 50 runs, okay. And there's basically no difference between the 40 and 50 run result. So by the time you've gotten to 50 runs, or by 40 runs even, you've saturated. You're not going to get anything different if you add in new statistics. Okay. Good. So I mentioned that we do things to make sure that we're not disobeying what we know masses to be from AME 2012. For example, the 2012 masses, we're training on that data, but we do even more. We consider different nuclear physics properties to make sure that we're not doing anything kind of funky in terms of the nuclear physics. So if we go to figure 4.
Okay.
Yeah, again, there's a little bit of a delay. I'm not at figure 4 yet.
It's okay. It's all good.
Okay, I see it. So this is a metric. It's defined in the paper, but essentially what's interesting to see here is look at n equal 82. There's this really big spike. Look at n equal 126, there's a big spike. So you see that where you have shell closures, you get some kind of enhancement of this feature, or of this particular, it's called the one neutron pairing metric. So this can have hints of structure in it, basically. But what we've done is to just ensure that we're obeying some basic nuclear physics properties through this metric. For example, we don't want a shell closure. There's not evidence of a shell closure in this region, so we don't let it get as high as these big peaks here. Mm-hmm. So that's one way that we constrain what we do to be physically relevant. Another thing that we do is you can see the 0 line there. There's never been a prediction or anything experimentally observed to be lower than 0. You do something weird in your predictions of nuclear pairing if you go below 0. So we implement that constraint as well. So essentially we're teaching the algorithm some basic nuclear physics, telling it not to go there to ensure that we have physical results. Mm-hmm. Okay, so that's the background on the statistical method and the kinds of information that we feed the statistical method. Now, I'm going to describe a little bit the astrophysics, the astrophysical assumptions that we put in. So here we explore 3 different types of conditions. Now we call them hot, cold, and cold. A hot condition is one where you have neutron capture and photodissociation competing for an extended period of time, and this determines your abundances as you go. So since you have this neutron capture in place, it's going to change how you evolve and also what types of species you're capable of producing. So we'll see that in the next figure. But also just quickly to explain, a cold is when you don't really have photodissociation competing. This falls out early, and you're dependent on beta decay to compete with neutron capture as you're producing heavy elements. So these are the types of conditions that we explore, and that's why the title of the paper mentions looking at our process dynamics. So we're looking at how is this actually proceeding, and then this tells you something about the types of astrophysical outflows that can in principle form the rare earth peak or be the dominant source of the rare earth peak. Okay. So if we go down to the figure.
Figure 5.
Yeah. This will give some visuals as to what those different astrophysical conditions really mean. Okay, so the red here is that hot condition, and the blue is the cold, and the green is that what we call a hot cold. We call it that because it starts out hot and then goes cold. Yeah, and it really, yes, and you can see the temperature as a function of time evolution of these is very different. The density as a function of time evolution of these is different. That's not in this paper, but that's also the case. So essentially, the top panel is the R process path, we call it. It's the dominant species at a given proton number that's populated at a given time. So this is right when we hit that 126 peak. So essentially, how far out are we when we enter this lanthanide region where we're going to form the rare earths? And you can just see this hot condition is closer to stability than the others because you have that photodissociation keeping you. When you don't have that there, you can go further out. So it's very distinct, it's very different. You're going to operate in different regimes of the nuclear chart, dominantly synthesize different nuclei depending on the conditions. So this is how we're able to couple rare earth peak formation and conditions, because how is this dynamically forming in this region? So the bottom,
let me ask a question. Where do the temperature and density profiles come from? Because those are not like, they got bumps and wiggles in it. So it tells me it's not some sort of an analytical.
Well, we put reheating in them, and that's why they can have bumps and wiggles actually. So that's why there's bumps and wiggles, but they are parameterized at the start in terms of entropy, time scale, and YE. And so your entropy is what links your density and your temperature for those who don't know, but then we have to include the fact that nuclear reactions release heat, and then that gives you your wiggles.
I'm with you.
Okay, so figure 6 is, to me, as somebody who's used to looking at timescales, astrophysical timescales, probably the thing that highlights the most that one is hot, one is in between, and one is cold. So what a timescale is it goes like 1 over a reaction rate. And then we sum this up and take a weighted, an abundance weighted timescale for all the nuclei in the network. Usually you see this as a function of time, but here we show it as a function of temperature because you can really see the distinction between the 3 cases. And you can see that green one, that hot cold one, really is in between. So you can see that let's look at the red lines. You can see that the neutron capture, the solid line, and the photodissociation are competitive for quite a long time before they break off there. Mm-hmm. And it starts out to be competitive for the green case here. It starts out competitive and then breaks off.
Yes.
with respect to beta decay. And then if you look at the cold, it's breaking off, you know, quite earlier. So you can really see what we mean by these sort of buzz terms, hot, cold, and so on from these timescales. I think it's really enlightening. And you can see that we've explored very distinct timescales then by looking at these three distinct dynamics by looking at these three conditions. Okay. All right. So that's our premise. We're gonna do this Monte Carlo for all of these three different conditions, and I'm about to talk about the results.
Cool.
Okay, so we can go down to the first figure, or not the first figure, figure 7.
First results figure. Yeah.
Yeah, first results figure. Yeah. Okay, so as I mentioned before, you're going to see these plots as our mass predictions minus the Dufalo-Zucker mass predictions because of that parameterization earlier. So are we significantly being different from Dufalo-Zucker, and in what way? So what I want to point out here is that we have only fed the algorithm information from AME 2012. All of the other data on here was independently measured. And this was done so by a collaboration, the CPT, Canadian Penning Trap, at Argonne National Lab at Caribou. So they went out, they asked us, you know, what mass measurements do you need in order to understand the rare earth peak? And these studies helped to guide what they would go out and try to measure. So this was in collaboration with experimentalists to really try to understand rare earth peak formation. So really powerful stuff when you put together nucleosynthesis studies like these and measurements. And then you can see the projections for future FRIB and the Argonne N=126 factory. So they're going to push out further and further to sort of tell us more information about the masses in this region, which are intimately linked to structure and, as we've talked about, rare earth peak formation. But what I want to highlight here is, again, like I said, these are independent. So we have a pretty darn good match going on here for this, what we call hot condition. So thus far, we're consistent with their mass measurements. So this condition could be something capable of forming the rare earth peak and matching the latest measurements. The most important feature, however, that we see in these masses to form the rare earth peak is at neutron number 104. You see this dip here, that dip right there. That is what causes us to have an enhanced stability in this region where we get pileup of material. And figure 8 like explicitly shows this, that we take and we do, okay, what if we just put in what we have at 102? What if we just put in our little mass difference at 104, at 108, etc.? And you can really, really see that this 104 is strongly responsible for piling up your material there. 102 helps to keep it in the proper, to move it over to the proper location later as the synthesis, as the process proceeds. But nevertheless, this 104 is really dominant. So we're really excited that future experiment can get out here and be able to say something about whether or not this this matches up. Okay. All right. Yeah. So if we go to figure 9 now. Oh, not 9, it's 10.
It's all good.
Sorry. Yeah. It's the big, yeah.
Ooh, the big one. Okay.
Yeah. Yeah, you might have to zoom out for that one.
There we go. Try that.
Exactly. Okay. So this is just to watch how this formation of the rare earth peak happens in real time with that mass solution that I just discussed. So the top panels are in early time, where those are your abundances on the left compared to solar data. And on the right, that's what we have going on in the NZ plane is what we call it. So you can see the proton number and neutron number explicitly. The red, again, is that our process path, the dominant species populated at a given time. And the black boxes are what you would get if you just assumed you have N gamma, gamma, N equilibrium. So you can see that we're following that really closely at the beginning, like exactly pretty much at the beginning. Okay, then at the middle time, you can see even at these middle times, we're following this N gamma, gamma, N equilibrium, and we're starting to pile up. Frank had his cursor like near that pile up over there. We're starting to get this pile up, and you can see explicitly when you go to the right panel that it's at that neutron number 104, where we're seeing this pile up. So this is what's happening in that region because of our mass adjustments there, because of that little dip that you saw. You have an enhanced stability that you've introduced in your reaction rates, and you have a pile up there. And then later, we're just going to start to decay back to stability. And this is all going to start to get smoothed out by beta decay. Everything in the right is colored blue if it's dominantly undergoing beta decay. Is what this figure is. So we're just going to start to beta decay and smooth all of this out, but we still stay enhanced is what's happening. So that just explains more of how this is evolving for this particular case and why this works. Okay, so if we go to the next figure.
Good. 11. And possibly 12. We'll go stay with 11.
Yeah. So these are our results for when we take a look at that cold astrophysical condition, that one that went more towards the neutron drip line, further away from stability. We do have a dive to try to produce an enhanced stability, but it's in a different location. So it's not at this 104, it's different. And we can also see that we don't quite touch that CPT data point there because we don't really have to do a rise and then a fall. It's very different structure that's needed to form this peak. Okay. And you can see that explicitly in 12. Again, yeah.
Yes.
Yeah. That, yeah. Okay, sorry, there's a little bit of delay. But in 12, you can see that we looked again at exactly what features are really most responsible for peak formation in this particular case. And in this case, it's at a higher neutron number. It's actually at 108. That is the thing that's of most relevance to us. And that makes a lot of sense if you think about, again, that plot where we had the paths at the beginning. If you're more towards stability when you start, then you just need to be able to adjust what's happening with your abundances at higher neutron numbers. Okay. So that's what we saw with this particular condition. And if we go down to, the big figure where we explain all of the dynamics. Yeah, so this just highlights the top panel here, really shows you that you're never quite in that N gamma N equilibrium. Like it just never happens. This is what a cold case does. So, and you can also see from the second panel, this initial pile up at 108 trickles backwards. So when you go to the right panel here, yeah, exactly. You can see that initial pile up at 108, and then that keeps feeding backwards. And in the next panel, that's fed backwards to 106, which feeds backwards to 104. And then at late times, it gets pushed into place. So in the last figure, you can see that now we're piled up at 104 at the end, but to get there, we had to initially pile up at 108. And then it's off center for now, but there's going to be a lot of late time neutron capture pushing this peak into place. Right. So this is really just highlights the very different ways in which the R process proceeds in these types of conditions. So it's very, very distinct dynamics. Okay, so we can move on. The next section is all about the hot-cold condition, but essentially everything that we've said here is you can get the picture of what's going on from what we just discussed. But the point is, again, it's a different predictions for what features really matter to form the peak here. Here it's at 106. So that's different. But otherwise, yeah, exactly. It's at 106.
Yep.
Okay.
With you.
Yeah. So we can now just go to where we're going to start comparing these things in the next section, because we already talked a lot about the dynamics, and hopefully that's very clear, but we show the dynamics here. So we can
still get this pile up eventually.
Yeah, exactly. But it operates a little bit differently, and yeah, right. But the same types of arguments hold. Okay. Yeah. So this table too is just a reporting of the different statistics, essentially the baseline chi-squareds, where we centered our mass measurements, the average chi-squared at the end, average number of steps, acceptance rate range. So for the people listening that may be interested in statistical methods and doing things like MCMC, check your acceptance rates. This is something that's really, really important to make sure that you're moving around the parameter space. When you have a lot of parameters, you want to be, at least like 30, between 20, 30%, up to 50% is okay, 50, 60. But if you're at like 1%, you're not moving around enough. That's a key thing to look at. And then we've also listed what's most influential for the main peak here. So that's just to compare them. But you can see in general, statistically, we made sure that things were similar. We made sure that we were running for similar amounts of steps. We had similar acceptance rate ranges. So the differences are really, really coming from the different astrophysical conditions. And this is what makes our results really informative as to the astrophysical conditions. Okay. Cool. Okay, so let's move on to figure 19.
Okay.
So in figure 19, what we did was to say, okay, great. We have all of these different solutions, but what if every one of them worked in every condition? What could we really say? I mean, it doesn't seem like that would be the case, given all of the different dynamics that I just explained and how everything is really linked to how the R process is proceeding. But, let's double check it. So in the first figure, we took and we put all of those mass solutions into that hot outflow condition. So of course, the red solution is doing great because that's what it was designed to do. But the other two produce a peak, but it's way off center. It gets completely pushed. Actually, yeah, that one right there. It gets way too pushed. So it's just not going to work. That kind of solution will not work in those conditions. Okay. And then you can just see we did the same type of thing. We put the cold solution in all of those different scenarios. And then we put that hot cold solution in all those different scenarios. So you can see that although you get pile up with the different things, they're not quite in the right place, or they're not really doing what they should, right? You need something that's tied to the dynamics. So they do distinct solutions form the peak in distinct ways. Therefore, when you take these solutions and you compare to the nuclear physics, you can say something about what type of condition is matching with rare earth peak formation and the latest nuclear physics data. So this is what we did in figure 20. So all of the figures that we've seen up to this point for these mass predictions were for neodymium. They were for neodymium. But our colleagues at the CPT also took a look at samarium, which is, so for reference, neodymium is a Z of 60, and samarium is a Z of 62. Okay. So it's higher up, so they were able to go a bit more neutron-rich. And when you do that, they were able to get out to n equal 102. And we see that we don't really match what they see with anything but that hot case. So it's really this hot case that is most consistent with what they're seeing right now in terms of mass measurements. Now, this hot case was really, really sensitive to 102 and 104. So it's pretty significant that we're matching at 102 there. Otherwise, you might be able to say, can the hot case really work if they didn't see this 102 feature? Right. But for the cold and the hot cold condition, we really, as we pointed out, we need some higher neutron numbers. So those were really forming the peak at 106 and 108. Right. Those are really, really where we want some measurements in the future. So I'm super excited, future measurements. Do we see this drop at 104 for the hot case? What's going on at 106? What's going on at 108? So can we do future measurements support any of these mechanisms? And if they don't, then you can say something about at least the dominant type of condition that formed the rare earth peak within our solar system. So that's really, yeah, that's the fascinating bit here. So this focused on dynamics, but you can hopefully eventually map this back to sites through simulations, because we're looking at the dominant type of condition. So if you have a simulation that's just dominated by this cold like ejecta, is it something that can really be responsible for the primary production of lanthanides in the solar system? And I think, you know, we need more measurements to be sure, but so far the hints are looking like it's the hot case.
Yep. Very cool.
Yeah.
Nicole, thank you.
Thanks.
Yeah, you mentioned, I think, so going on the measurements, you mentioned in an early figure that there was, you know, FRIB coming up. And so there's FRIB year 1, year 2, full strength. You mentioned the N equal 126 argon factory. What's sort of the time scale for those to come up? Are we looking at something over the next year, the next 5 years?
Yeah, so the first FRIB proposals are going on, right? We're just submitted, so that's extremely exciting. So yeah, FRIB is scheduled to come on in 2022. I don't know, you know, an update from that given the situation. I'm not quite sure. As far as if they, so for day 1, they can reach a lot of these things. They'll be able to produce a lot of these things of relevance. As far as whether the experiments will be in place to actually go after them, like the most neutron-rich measurements, that remains to be seen. There's a lot of proposals out right now, and we'll see. So timescales of actually getting information are a bit more uncertain, sure. but FRIB will turn on within the next year or 2.
That's great.
Yeah, it's very exciting stuff.
There's going to be a lot of action in this field, I think, over the next 5 years. So
yeah.
So if you look in your crystal ball, so you've got some new nuclear measurements coming on, terrestrial measurements. Are there other aspects going on over the next 5 years that could be informative? That could be you know, new observations of, let's say, neutron star mergers, or
of course,
a nearby supernovae, go Betelgeuse, or calculations. So just if you look in your crystal ball over the next 5 years, where do you think the community is going to be headed?
Yeah, I really think there's a lot of opportunities to interface, as I've tried to highlight here, between these advancements in nuclear physics and observation, definitely. More kilinovae would be nice, definitely, but who knows? I mean, we've seen more neutron star mergers, but we haven't gotten that electromagnetic component. So that's the tricky part here. Are we going to get an electromagnetic component? One interesting thing is also, I had a recent co-author paper where we looked at gammas coming from fission for a neutron star merger in this galaxy. Now that's, who knows if that could happen, but if it does, there could be some really interesting signatures there. So I think that there's a lot of opportunities with kilonova, with gamma ray astronomy and things like this. Also stellar data, looking at stellar trends. That our Process Alliance is getting more and more our process enhanced stars all the time. Yep. This is really, so in my crystal ball, I see a wave of new data, as you mentioned, cool, from many aspects. And I really look forward to being somebody who can do my best to synthesize all of this to tell you guys what it means.
Very cool. Very cool. Awesome. Nicole, thank you so much.
Thanks, Frank.
All right, everyone. Thank you. And we will see you on the next one. Bye-bye.